Okay. You guys have any questions from this remaining portion, or you guys are good? Did you solve this? This is called the 2-point Arrhenius equation. Two-point Arrhenius equation. All you need to do is to set up the values. This is a part A first. So this is what we call the Arrhenius 2-point Arrhenius equation. There is an equation that we get. I've already discussed that we can plot the data. We can get the linear line where slope represents EA minus EA over R. It's going to be a negative slope. So if we can get the value of minus EA over R from the Excel curve, Y is equals to MX plus B. So M is going to represent this. So that value will be available to us. So we can multiply that value by R and we can get the activation energy. But if only two data points are given to us, we're going to use the 2-point equation that is here. And if we are trying to calculate the activation energy, this is the rearrangement of the equation. Okay, so you can do this, you can use the same equation, or you can use the rearrangement to find out the activation energy. In this question, it says calculate the activation energy of the rate constant at 555 Kelvin. The rate constant at 555 Kelvin is 3.5 to 10 times to the power 7 liter per mole, which is molarity. So two rate constants are given to you and two temperatures are given to you, asking for the activation energy. I think we covered it last week. So that's how you can cover, so all you need to know is that R is in joules. So yes, there is an in-person lab today. At 1 p.m. we are meeting in the lab. This was posted approximately a week ago. And the assignment is on Canvas. To print those lab, there are 2 assignments for today. To print each of those lab reports and bring it to the lab. There is a pre-lab activity. Just finish it before you enter into the lab or sitting outside. It's just the dilution calculation that you are doing in that one.
And Professor, those are both the lab 4s, right, on the assignments?
Yes.
Got it.
There are 2 parts. There are 2 assignments today.
Got it. Yeah.
It says lab 4 twice on Canvas. Okay, so here you're supposed to just plug all the numbers in, use your calculator to find out the EA. That will turn out to be 4.7 times 10 to the power minus 4 joules. In this question, it says the reaction has an activation. So activation energy is already given to you, but mind it that it's in kilojoules and the R is in joules. So do not forget to convert this into joules. So it's going to be 81,000 joules that you are supposed to plug into the equation. To plug that in here, okay, and the temperatures are given to you in degrees Celsius. So you have to convert those into the Kelvin because this is Kelvin here. That's all you need to do, and then plug the numbers in and just solve it in your calculator and get the answer. Sorry for this one. That is not the that's not the activation energy pin. So I'm going to erase this part first. (1.8 times 10 to the power And that will be the rate constant, which is going to be per second. Next part is reaction mechanism. So what we have learned earlier is that we can just give the rate by looking at the chemical equations, mostly by just looking at the reactant. We do not really need to look at the products. But now what we'll see is that determining the rate law is even more complicated. Okay, in most cases, because a simple equation that we see is for the chemical reaction, we just see a balanced chemical equation, right? So it's just a direct change, but that change may have taken multi-step process. There might be some more equation before the final products have appeared. So it says this that you see it directly, but it's not as direct as you see is in just one equation. So what it says, the chain may have taken multi-step process and with different translational changes, different what you call the intermediate substances have formed, which have been decomposed or been rearranged into the final product. So we have to figure out the preliminary steps. So the intermediate steps in any reaction, we call them preliminary steps. So as you see here, there might be reactions involving only one reaction. There might be reactions involving two reactants and more than two also. So mostly we look at the unimolecular and the bimolecular reaction. We already know that the collisions are happening. So this is molecularity, which says the number of things that must interact for the reaction. And you know, the orientation of reaction is also very important. So what you see here is you see a direct chemical reaction here, but it has an intermediate step where this and this is first going to go into this, and then finally is going to go into the product. So you do not see this anywhere. This step you never see anywhere in the direct equation. This is called the intermediate step. The mechanism of a chemical reaction solely depends on one of the intermediate steps, because that in these steps, there is going to be a rate determining step, a step that controls the rate of the reaction, how fast it is going to be, how slow it is going to be. So if you know the mechanism, what is an intermediate step that is playing its key role in the rate of reaction, you can always have a control on it. That's what we call elucidating the reaction mechanism for the rate laws. It's not very easy, okay? And like big scientists do that, but we understand that there is a mechanism involved, there are intermediates involved, and then one of the intermediate steps or the preliminary steps that we're talking about are going to be, one of them is going to be the rate determining step. Rate determining step is one step in multi-step reaction mechanism, which is significantly slower. So the slower one is the key player, and that controls the mechanism. Okay, the intermediate reactions they are talking about, and reaction cannot proceed faster than its slowest step. Okay, so keep that. So what are we interested in? We are interested in the rate determining step, and the first step in some of the reaction, the first step is going to be the rate determining step, and in some of them, second one is going to be the rate determining step. How come one and second? So these are the, let's say these are three preliminary or intermediate reactions which are happening in order to give us this overall reaction. So what we see this one as a balanced chemical equation, but actually this is happening there, this is happening there, and this is happening there behind the curtain. So out of these three reactions, when we add them all together, we're gonna find the equation of interest. So this, out of these three, there is one which is slowest one out of three, and that is the rate determining step. So the mechanism below has been proposed, like scientists have discovered that these are the two steps happening for a particular reaction. What is that reaction? Reaction is between carbon monoxide and nitrogen dioxide. What is the overall reaction? If the first step is the rate determinant step, what is the rate law expected for this mechanism? So there is a condition that the rate law may never have, it will never ever have the intermediate steps, intermediates in it. So make sure when you're writing down the rate law from these two equations, it needs to be, it must go with that condition. What is that condition? That the intermediates will never be there. So I'm going to write it down. If I say, if I write down the rate law for the first one, what will be the rate law for the first one, where we have nitrogen monoxide, nitrogen dioxide, and we have so it says what it says here, rate determining step. So the first step is the rate determining step, and the rate, because this is controlling the rate of the reaction, we're going to write down the rate law with this equation. So if we look at this as reactants here, then it's going to be, the rate is going to be equal to K times NO, right? This is how we write down the rate law. So we see that the intermediate is not involved, and this is the rate determining step. And when we write down, if this is the expected rate law. So in the expected rate law, you will never have the intermediate, and I see the intermediate here. But the condition, if the situation reverse, and if the first step is not the rate determining step, and the second one becomes the rate determining step, then you'll have to write the intermediate in your rate law, and that is not acceptable. Okay, they have made it in a way that it is not acceptable. So the forward and the reverse reaction of the first step are very fast compared with the second step. So the second step is the slowest one, is going to be the rate determining step. So the initial reversible reaction is said to be in equilibrium, where rate 1 is equals to rate 2. What does that mean? So if you're writing it as NO2 plus NO2, I skipped this NO2 here, and that reminded me. So NO2, NO2, and then, so for a reversible reaction, now we are talking about the reversible reaction. Okay, you're looking at things differently, but this is the fast one, right? So if you look at the fast one versus the slowest one, is the other way around. So this is the slow at this time, and this is the fast. So we have, because these are two reactions, so two rate constant are playing their role. K1 is going to be the rate constant for the forward reaction, and K inverse is going to be the rate of constant for the reverse reaction. Okay, so we are talking about K1 over K inverse for this reaction. And if we are looking at the second equation here, which is actually the rate determining step, trying to talk about, we're talking about this. Okay, when I'm talking about this here on top, I'm talking about this. There's going to be a K1, and there's going to be a K inverse for this. So we can write down actually two rate expressions, like K expressions for that, right? And when we are trying to write it out, but for the so this is the third one that we are talking about, right? And if we write, and this is the rate determining step, so we are mostly interested in this. So when we write down the rate law for the rate determining step, and for this we can call it the K2. Okay, so K1, K inverse, and K2. So if we look at the K2 and we write down the rate law according to the RDS, then rate is going to be equal to K, and then I will have NO3 here, okay, which is an intermediate. and then I will have carbon monoxide here. But that is not allowed, okay? The scientists have devised a way that intermediate, because intermediates do not control the rate of reaction. So what they have done, they have substituted it, okay? Intermediates are not allowed because they are not actually involved in determining the rate. These intermediates, reactants are involved in. So what we do, we just substitute that in this part where the second mechanism, with the second step is the rate determination. Because it's not allowed, we have to replace it with something else. And that replacement requires us to play with equation 1. And that is where we are going to write rate 1 is equals to rate minus 1. This is for the forward reaction here and the reverse reaction here that we are talking about here. So if we write it down, it's going to be, this is for the forward one, and this is for the reverse one, or the backward one. So if we write it down here, that's going to be for the top one, right? That's going to be K1 over NO2 square, because it's the same thing multiplying there. That was a mistake. Now you can multiply these two together over the reverse one, which is going to be here. Next is going to be for the reverse one. For the reverse one is going to be definitely K minus 1. You have on top, you have NO3 and you have NO. We can get rid of K minus 1 here by dividing both sides from K minus 1 and K minus 1. And that's how we're going to get rid of this stuff here. And then you can come here, use this space. And we can say, if we look at this one here, we can say now K1 over K minus 1 and O2 square is going to be equal to NO3. What else was there? NO2. So actually we can have a value for NO3, and that will be the NO goes down there, right? So that's going to be K. That's going to be K1 over K minus 1 and O2 over, that NO2 goes down there, and O2, I have to erase this part. And then that's going to be equal to, so we got the value of NO3 that doesn't have any intermediate in it. And then we just need to substitute that in the rate law. And when we write down the rate law, it's going to be, so we know that it's going to be rate equals to K, and then it's going to be NO3, and it's going to be CO. We need to plug this in this here. Okay, so it means we are trying to talk about the rate of K2 here, so that becomes K2, right? Because now we are talking about the slow step. We have used the first step to get the value of N3. So then it means it's going to be rate is equals to K2. Then what I'm supposed to put in is K1. Let's make a parenthesis and say K1 over K minus 1 and O2 over NO2. Let's close this and say CO. So we can sort it out. We can say that all this that I have here, which is K, this thing here. Let's fish that out just to make it simple. Okay, we can give it a name, another name. We can call it K. So K is equals to K2, K1 over K minus 1. So we can just replace all of that with K. I can say that it is going to be, the rate law is going to be finally rate is equals to K, and that's going to be NO2 to the power 2 CO. And then that's down here is going to be NO2. So we have to write this rate law because the rate law never takes an intermediate in it. What is the rate determining step for the reaction depicted in the energy coordinate diagram? The slowest step is going to be the rate determining step. Which one is the slowest one? So catalyst, a substance that increases the rate of chemical reaction by lowering the activation energy. So it's simply lowering the activation energy without itself being consumed. So it's inert. It never takes part in the chemical reaction. The good part is it can always regenerate and reuse the catalyst. Okay. Sometimes the catalyzed path contains multiple steps. Okay. So you have to determine the mechanism once again. If you are using a catalyst, it's going to be a different process for all over. So if you look at the chemical reaction, which is catalyzed versus uncatalyzed here, you see that the pathway is changed for a catalyzed versus an uncatalyzed pathway. And that brings, for example, multi-step process. This was just one step versus 2, 3, or probably was 2 steps, then it becomes 4, 5 steps. But it actually does, it reduces the amount of activation energy required for the chemical reaction to happen. This is also, you can compare here. Always remember the energy is on y-axis and the progress of the chemical reaction is on x-axis. Types of catalyst, homogeneous versus heterogeneous. Homogeneous is when you have all the reactants in the gaseous form, and then you using the gas, the catalyst that is in gas phase, that is called homogeneous catalyst. Whereas you are using gases here, we're using a solid catalyst in that one, that's called the heterogeneous catalysts. Different than the reactant, the physical state of the reactant and the products. That's all it is. And probably you have already covered all the materials. So what's just a review for you guys. So moving forward to chapter 13, which is like a very fundamental concept in chemistry. And this concept must always be clear because next few chapters like 14, 16, 14, 15, and 16 are mostly going to revolve around the concept of equilibrium. Where is this concept coming from? You have just seen that from talking, we were talking about the chemical reaction that goes in just one direction. So we have just started talking about the chemical reactions going in the forward and the backward both. So this is just one direction reaction. And now we are moving towards the reversible reaction. So most of the reactions in chemistry are reversible reactions. So now this, when it comes to the equilibrium, it is always about the reversible reactions. So the two examples of this reaction that I'm talking about here right now is it's important to notice that the chemical reaction that come across most of the time to us, we do not pay attention to that, but they are actually so let's talk about the reaction of HCl with water. what will happen? So you're gonna have H3O plus, and you're gonna have H2, sorry, and then you're gonna have chloride negatives. You know this is hydronium ion. When the hydrogen comes out of hydrochloric hydrogen chloride gas, it's going to react with water molecule, and water is going to take up a hydrogen on it. It's going to become H3O plus. We call it hydronium ion, and the chloride ions are also there. Versus you have CH3 COOH, which is acetic acid that goes in. When you reacted it with water, it's not going to be a single-sided reaction. It's going to be a reversible reaction. And again, you're going to make H3O plus, and then you're going to make CH3 COO negatives, which are acetate ions. So these are chloride ions, which is an atomic ion. This is acetate ions, which means you are talking about a polyatomic ion. Hydronium ion is also a polyatomic ion. So the difference lies here, exactly the way I was talking about. This is just a one direction reaction. It's going to go all the way to the forward and never comes back. But this reaction is different because it always goes into the forward direction and then moves back to the reverse direction, because it is so what it exactly means is that there's going to be a concept of equilibrium involved. And what is that concept? Is that at one point the process becomes so synchronous that the net change in the concentration of there's no net change in the concentration of the reactants and products. It doesn't mean that the reaction is not happening. It doesn't mean that the reactants and products are at the same concentration. All it means that it is being formed synchronously, that there is no net change. Let's talk about it's extremely important to understand the equilibrium, because a lot of physiological process involve this equilibrium. Like if the and disturbance in equilibrium is also important, because the process is not going to happen, and that requires the shifting of chemical reaction from one side to another side. So chemical equilibrium that we are trying to talk about, then there is a concept of equilibrium constant. Remember that this is equilibrium constant, not rate constant. That story is done. The rate constant story is done with the kinetics. Equilibrium is all about equilibrium constant, which is capital K. This was small k like this. So that keep that difference in your mind. Okay, moving forward, we need to know the chemical equilibrium, the basic and the fundamental concept of equilibrium constant, and we must know what the equilibrium constant and what it is going to talk about the chemical reaction. So, guys, it means we are going to look at a chemical reaction that is in the reverse direction. It's a reversible process. So, calling these substances as reactants and as products becomes arbitrary then. Because at one point, a chemical reaction is where the products is going to start going backwards. And at this point, this becomes reactants and this product. So initially, these were the reactants, and the process was going in the forward direction. So these were called as products. And then it's all the way when the concentration of the products goes up, they become reactant and they start converting into this part here. So actually, we cannot say which one is. At one point, we can say this is reactant and this is product, but this straightforwardly in general calling them, we can start reaction from anywhere. We can start reaction either from this side. We can just take D and E and start the chemical reaction. So we'll form A and B, and eventually A and B will start converting into D and E. So that is there's no bound on it. You can do anything you want to in the reversible reactions. Okay, so from single one direction reactions to the double direction reaction, or the reversible reaction that we always talk about. So here you are looking at two things. When is the equilibrium achieved? The equilibrium. So when we are talking about two different, and this is exactly what you know, that the rate constant is going to be 2, K1 and K2 for the reversible reaction, right? In the reverse direction. So Equilibrium is when the rate constant of the forward reaction becomes equal to the rate constant of the reverse reaction. Exactly what we are seeing here. So that is the rate that we are talking about. Rate, this plot is showing the rate of the reaction, and this is showing the concentration of the reaction. So for sure, NO2 is our product in this chemical reaction. So as the time proceeds in the chemical reaction, the products will start appearing and the reactants will start depleting. But there will be one point where there will be no change in the concentration of either the reactants or the products. That is where we say equilibrium is achieved. That was based on the concentration of the reactants in the product. When it comes to the rate of the reaction, so what happens? The rate of the reactant is going to go down and rate of the product is going to go up. And there will be a point when both of these reactant, the rate of reactant and the rate of product, or rate the correct terminology will be the rate of the forward direction to the rate of the reverse direction becomes same. Okay, it's equal. So that is the equilibrium point. So what does that mean? That when we do this kind of experiment, the reverse reaction occurs. We know that. Okay, so when if we are looking at and there are ways to calculate the rate constant that you're already familiar with. So you can actually calculate the rate constant, and you can talk about what is going on in the chemical reaction. If the two rates are equal to each other, then you will say, okay, the reaction is at equilibrium. So establishment of equilibrium that we have just discussed is that C for the reactant and for the product, what is going on. This is the chemical reaction. This is I'm going to start with this. So that will be called as product at one point in the reaction time, the concentration versus the reaction rate. So this story is all written here. Common equilibrium misconception, as I have already explained, that never say that the system is a static. System is not a static. It is at equilibrium. And that means it's not halted. It's not a stop. It's so synchronous. It's happening in that synchronicity that the concentrations are not changing. Okay, so the amount of reactant and products are ordinarily not equal to each other. The amounts are not equal. They are not changing is a different story, although the amount of reactant in the product remain constant. Whatever the concentration for the reactant is, whatever the concentration, these two concentrations are not equal. So equilibrium constant is an expression, or is a value that we calculate to see where is the reaction happening at one point. So am I here in the reaction, or I'm here in the reaction, or I am exactly at this point in the chemical reaction? We do use equilibrium constant, and we do calculate the value of equilibrium constant. So it's called K, but at equilibrium, it is the value of it is going to be called K. Anywhere else from so if it's equilibrium here, it's called K here, or if it, again the equilibrium is disturbed, it's not gonna be the K. We use it as a reaction coordinate. We call it Q. So Q is equal to K. We are doing the same thing, but at equilibrium we're gonna call it the K. At anywhere else besides equilibrium in the reaction, we're gonna call it the Q. So consider the general reaction that is exactly like this. So these are either gases or aqueous, and ABCD are the mole ratios. How do we write the Q expression? Or how do we write the K expression? It's always going to be the products divided by the reactants. And it's the product of if you have many products, then it's going to be the product of each of them raised to the power of their mole ratio. So if I'm writing Q expression or K expression for this chemical reaction, that's going to be QC is equals to, my products are here, and because they are gases or aqueous, they're going to go into the expression. If they are liquid and solid, they will never appear in the expression. So it's going to be the C to the power C, and then D to the power D, because D moles of that. And then reactant goes down here, so it's going to be A to the power A, times B to the power B. As simple as that, because all of them are either gases or equals, they will be included in the expression, otherwise not. So all concentrations must be in molarity. Product concentrations are in numerator. Do not forget that these powers are the mole ratio that you have in the balanced chemical equation for them. So the value of the reaction quotient, what does that mean? When you calculate that, dividing the concentration of the product at any time in the chemical reaction versus divided by the concentration of the reactant at that time in the chemical reaction is going to give you some information. So the numeric value of QC for a given reaction can vary prior to equilibrium. And the value of QC depends on the concentration of products. And this is what we are taking. We are taking the concentration of product on top divided by the concentration of reactant. So that tells you the ratio of what is going on. We can only calculate QC at any point in the reaction. We'll often calculate QC at the start of the chemical reaction using initial concentration. And there's more to it that you can read at your own. I'm trying to tell you that this is exactly the Q. So there's no difference. It's just the thing that you are doing at equilibrium is going to be called as Kc. So Qc at equilibrium is Kc is exactly like this. Just change Qc to Kc and you will get the value of equilibrium. Do not confuse with the kinetics rate constant small k. That's again written here. So make sure that you're reading. So the equilibrium constant K, the magnitude of this constant is going to tell you the progress of the chemical reaction. Okay, it is independent of the starting amount of reactant. So the initial concentration has nothing to do with the value of equilibrium constant because it's just the ratio of products over reactants. You know that. The value of equilibrium constant is dependent on the temperature of it. It affects. When it's about the temperature, it's going to affect big time the value. So besides that, nothing is there that can affect the value of the concentration of the reactants and the product has nothing to do on the value of equilibrium constant. But yes, if you change the temperature, it will definitely change the equilibrium constant. The magnitude of an equilibrium constant indicates the extent of the reaction, where it lies at one point in the chemical reaction, where you are calculating. You got the concentrations from there, and you are calculating the Q. It might turn out to be K. So K and Q are unitless values. Even you see when you're doing the calculation, there's a unit left, then you're supposed to drop it because K never takes or Q never takes a unit with it. If the K is very small, it means it's still most of the stuff is in the reactant form. Okay, it's mostly reactants. It means reaction is not proceeding towards the products. But if the K is very large, it means most of it has already been converted into the product. So the reaction is it's product heavy at that point. The value of K gives no indication as to whether the reaction is fast or slow. Keep that in your mind. Never ever. Okay, so less than one, more greater than one favors products. So we calculate the value where the value is going to lie. Less than one or more than one favors reactants and products. This is what we're supposed to figure out. So how we can write down, we can easily write down the equilibrium expression now. Everything is in the gas form. Need to pay attention to that. That this is gas, gas, gas. So expression K is equals to the products goes on top and H3 raised to the power 2. Do not forget that. That is the that is a very common mistake by the students. Then you're going to take H2 raised to the power raised to the power 3 and 2 raised to the power nothing 1. So then what do we need? We need the if we want to calculate the K, we need the concentration of each of them at equilibrium. And then we can plug them in and we can calculate the K to see what is happening. So Q and K and the direction of the reaction is what we are interested in. So a system that is not at equilibrium will proceed in the direction that established. That is the intrinsic property of any chemical reaction. They would like to go towards any reversible reaction would like to achieve an equilibrium. So even if there is a disturbance in the equilibrium, the reaction will again move in the direction to wherever it is supposed to go to attain the equilibrium. So we can compare Q and K, and we can determine which direction the system will proceed. So if Q is equals to the K, the system is at equilibrium. If Q is greater than K, the reaction will move from the right to the left. Q is larger than K means more products are there. So it's product heavy. Q is less than K means the reaction will move from the left to the right. It means it is reactant heavy. Q less than K is reactant heavy. Q larger than K is product heavy. So if it's product heavy, it's going to move towards the reactant side, which is right to left. And if it is product heavy, then it's going to move from, if it is reactant heavy, so it's going to proceed in the forward direction, and that's going to be from left to right. Working with the K, yeah, this is important. If you are trying to do the relationship of K, the K of a if the K of a reaction in reverse is going to be the inverse of the K of the forward reaction. The K of reaction that has been multiplied by a number is equal to the original K raised to that number. And K for multi-step process is the product of Ks of those steps. You have to add those steps, but you have to multiply the K value. So use the information below. So there are two reactions given to you. For them, the equilibrium constants are given. It says use this information that you have here to find the K value for this equation. What does that mean? It means that this is not easy to calculate the K value for this chemical reaction, but we have some other steps that we can follow and get the K values for. Once we are done, we can rearrange these two equations, add them together, and we can take the product of the modified version of the K values here. So in order to get the desired equation, I have to flip this equation, reverse this equation here. And when I do that, then it's going to become H2CO3, and that's going to go into H2O and plus CO2. So when I'm reversing this, the K is going to become K inverse, and that's going to be 1 over 1.58 times 10 to the power minus 3. Okay, do I need to reverse the top the equation 1 also? Make sure that this carbon dioxide here is in aqueous condition. And in the main equation, we have carbon dioxide in the gas phase on the right-hand side, which is right here. Okay, so I have to reverse equation 1 also. If I reverse equation 1, that becomes CO2 aqueous here, and that's just going to go, and then it's going to go K CO2 in the gaseous form. So then I can cancel this to that, right? But then before I'm doing it, I have to reverse this one also. So K1, this is K2 inverse, this is K1 inverse is equals to 1 over 3.36 times 10 to the power minus 2. So now I have to add this together to get the desired equation, which is H2CO3, and then it's going to be H2O plus CO2 in the gaseous form. Right? When I'm adding the equation, I have to multiply the equilibrium constant. So that means it's going to be, in order to get the K value for this equation, I have to do 1 over 1.58 times 10 to the power 10 to the power minus 3 times 1 over 3.36 times 10 to the power minus 2. So you'll multiply it and you'll get the answer then. What is the answer?
I had like 18,836.
Okay, it's a big number. Good. What is the unit?
Shouldn't it be unitless since it's K?
No unit. It's unitless. Correct. This is again is saying that the initial concentration has nothing to do. If you start with any amount of reactants or any amount of products or a mixture of any concentration of reactants and products, at the end, the equilibrium constant is going to be the same value. Concentration has nothing to do on the equilibrium's value. This is called homogeneous equilibrium versus heterogeneous equilibrium. Homogeneous, that we have been talking about, that when everything is in the gas, or it's going to be, everything means reactants or products are going to be either gas, or it's going to be gas, aqueous, or it remains as aqueous. Okay, if these are the conditions. But here what you see is something is not aqueous, liquid is not aqueous. So this is exactly the gas homogeneous, but this is heterogeneous. Okay, so when it comes to the heterogeneous equilibrium, we have to omit the liquids and solid because they have nothing to do. There's no concentration change for the pure water and the pure solids. So it means if I write down the K expression for this one, here it's going to be the K is equals to the products. I have two products here, so C2 H4, and it's going to be H2 here over C2 H6. I'm going to include everything. But when it comes to the heterogeneous reactions, there's going to be a heterogeneous equilibria, and for that I have to start with the products, which is H3O plus concentration, and then F minus concentration, and that's going to be over only the HF. No liquids are included in the K expression. Okay, so that's the difference. Keep it in your mind. Do not forget that. Gaseous chemical equilibria, because the concentration of the gases are usually represented with the pressure in atmosphere. So their atmospheric pressure is actually the concentration. So what we do, the way we were calculating the QCs, we're going to calculate the QPs now. Remember, we were calculating the QCs for the concentration in molarity. There is that QC. Right now, about the gases, we are talking about QP, and because there's a change in unit, there is a little change in the concentrations also, and that leads into to a different value of K at P versus K at C. You know, if you're using the concentration unit as as molarity versus the pressure. So there's a slight difference in the values. We can compensate that by doing this equation here. So if Kc is known to us, we can find out the Kp. If Kp is known to us, we can find out the Kc. The equation is this, where we have the R as a gas constant. The value for this is here. And temperature, that's why temperature will always be in Kelvin. These two things to pay attention to. And delta N, when we are calculating delta N, it is going to be the total moles, the product minus total moles. This is the difference of the moles, okay? Wow, it looks so weird. Total moles of the product versus total moles minus total moles of the reactants. You will get the value of delta N. So let's do this one. The reaction is this, is all gas, for which the Kp is given to us at 25 degrees Celsius, which is 298 Kelvin. What is the value of Kc at this temperature? Okay, so the equation is here. We have to calculate the delta N first, and delta N turns out to be product is 2 minus 4. 3 plus 1 is 4. So total moles, 2 minus 4 is going to give you minus 2. So the value of delta N is minus 2. So the Kp is given to us. We have to rearrange this equation, right? So it's going to be Kp over RT to the value, oops, this is not T. So RT raised to the power minus 2 is equals to Kc. So it means it's going to be 1.01 times 10 to the power minus 4 over 0.08206 times 298 raised to the power minus 2. So do that in your calculator, let me know the answer. Okay, so this is exactly what I talked about. Solid never goes into it, so it's going to be just this part here. So if I write down the K expression for it, it's going to be the NH3 times HCl. That's all. Calculating K. And we are working on the ice charts now. So moving forward, this is the chemical reaction. It says sulfur trioxide decomposes at 1000 Kelvin in a steel container. The partial pressure is 0.2 atmosphere. What is the value of Kp at 100 degree Kelvin? So this is not the question of Kp is equals to Kc times the RT over to the power delta N, because there is no Kc is given to you, so you cannot go for that. Here's what is it asking you for? Is asking you for the equilibrium constant straightforwardly. It's giving you the initial concentration of sulfur trioxide, and that is where you have to pick it up, that you have to go through the ice charts. Okay. So ice chart means that you have to sort out the information in a table like this, where, and I usually use the balanced chemical equation. So I write the reactants and products first. So that's going to be 2SO3, and then I can use arrow. I can omit arrow. It's up to you. I usually use arrow to keep myself in a position that it is, this is how it is. Okay, then I'm going to do what? I'm going to make this chart here, and I'm going to make 3 rows to it. The first one is going to show the initial concentration, the change in concentration, and the concentrations at equilibrium. So the initial concentration that I'm starting with here is the partial pressure. So the initial pressure is 0.500 atm for the, and we do not need to write units here, okay, for the sulfur trioxide. What is it saying? At equilibrium, the Sutu's pressure, so the equilibrium concentration is also given to you. What is that? Point, so equilibrium, at equilibrium, the concentration of this is, sorry, at equilibrium, the SO3 pressure is 0.500 200 ATM. So what is the difference? The change is going to be the difference, right? So that's going to be minus 0.3. And because the change, and now we have to look at the mole-mole ratio, because the mole-mole ratio remains the same. So the change, that was 0 and 0 initially, right? So then the change, because I have been able to calculate the change here, that's going to go into 1-to-1 ratio. So that means it's going to be the 0.3 here. So because from 0 to 0.3, it's going to be 0 plus 0.3 is going to be 0.3. And because this is 2:1 here, then it's going to go half, 0.15. And the final is going to be the 0.15 also. So that's how you got the equilibrium concentration for all of them. This is the concentration of SO3. And this is the concentration of pressure, which is, right, 0.3 is going to be the concentration of your SO2, and that is going to be the concentration of O2. So that was an easy way of doing it, because the equilibrium concentration of one of your substance in the chemical reaction was given to you. So you made the you did the stoichiometry here, and with the help of that stoichiometry, you were able to figure out the change, because it's 2. So it's going to be the same thing here, because it's 2 is 1:1. 2:1 is means you're going to get half of what you have here, right? So that's how we figured it out. Otherwise, there's situation where you do where none of the equilibrium concentrations are given to you. Then what you will do, you will again go through the equilibrium charts, like the example of this one here. Here it tells you that the initial concentration of PCl5 is given, but there is no equilibrium concentration given to you. So you have to go through the same stuff, the ice chart. So when I do the ice chart for PCl5, and then I do PCl3 plus Cl2, I need to go through this. What is given to me? The good part is that the equilibrium constant is given to me. We didn't calculate the value of Kp though here, right? We were supposed to calculate the value of Kp, because now we have the concentration of at equilibrium. We can do the Kp is going to be equal to the product is SO2 O raised to the power 2 and O2 and over SO3 raised to the power 2 again. Okay, so we did that part. So plug the concentrations in. If you plug the concentration in here, you're going to have it as 0.3. And you're going to have it as 0.15. And down there, you're going to have it as 0.3, right? No, 0.2. And then you can find out the value of Kp. We're going to do the same thing here. We're going to do ice chart here. What I'm going to start with is 0.275 molar concentration. And as I said, there's no need to add this here. Just make sure the numbers are correct. So initially this was 0. So now, how do I know what is the change? I'm going to go through, is it a balanced chemical equation? First notice that it is balanced or not. It is a balanced chemical equation, because I have to do this stoichiometry here. And in that way, I have to hypothesize, or I have to assume that the change is minus x here, because it's just one stoichiometric ratio here. So if this is minus x, this is going to be the x, and this is going to be the x. And then that's going to be 0.275 minus x, and this remains as x and x. So then what we can do, we can write down the rate expression Anyways, we can write down the, okay, we do not need that right now. It's 1 to 1 mole ratio anyways. So Kc, the value, so the expression is Kc is equals to PCl3 and Cl2, and then I have PCl5. So if I plug the numbers in, that's going to be 1.80 is equals to, I have x times x, which is going to become x squared, to the concentration of products, okay, divided by the concentration of reactant is going to be 0.275 minus x. And then how I'm going to solve this? Right here, right now, what I'm going to do, I'm going to rearrange this equation a little bit. And I'm going to say 1.80 times 0.275 minus x is going to be equal to x squared. And that turns out to be 0.495 minus 1.80x is equals to x squared, rearranging into the quadratic equation, x squared plus 1.80x minus 0.495 is equals to 0, which is ax squared plus bx plus c is equals to 0, right? So then where is the quadratic equation? It is here that we're going to use. So we're going to use only the plus version of the equation, which is x is equals to minus b, minus b plus minus b square minus 4ac over 2a. Will not work with the minus because there is no negative concentration, right? We are working on the concentration, so we're going to go with the positive ones only. So what is x? What is b? I know it already. My x here is okay, so x is going to be equal to minus 1.80 plus root 1.80 square minus 1 minus 0.495, right? Then divided by 2 times 1. You're going to be solving for this. The value of x will turn out to be 0.2423. You're going to now go back to your chart where you found out that the concentration was 0. For what? For PCl5, right? The equilibrium concentration for PCl5 was 0.275 minus x. So you've got the value of x, so subtract it from there. So that's going to be 0.0242 subtracted from there, right? And that turns out to be 0.0327 molar concentration for PCl5. And for, because it's the value of x is this, for the concentration of PCl3 and Cl4 is going to be this. So example 6, at a certain temperature, the reaction carbon dioxide gas is reacting with hydrogen gas, carbon monoxide, and this is being formed, which is example 6 here, right? So what are we doing? We are going to do the same thing. What it says, it's not giving you the concentration directly, saying 1.5 moles of carbon dioxide and 1.5 moles are in 5 liters. So you have to do the molarity for both of them. We never start with the mole. We start with molarity always. Keep that in your mind. So it's going to be 1.5 divided by 5.00 is going to be equal to the molarity. So when we start the chart, we will start with the molarity. So if I'm doing the chart here, so the molarity is going to be equal to 0.3 molar, right? 0.30 molar. So now I'm going to do and I'm going to use it right here. Okay. I'm going to do the charts here. Ice charts that I'm doing. What is the initial concentration of carbon dioxide and hydrogen gas is 0.30 molar. That's going to be 0 and 0. Then the change is going to be minus x. It's 1:1 already balanced equation. It's going to be minus x. This is going to be plus x and plus x. That's going to be again 0.30 minus x, 0.30 minus x, and that's going to be x and x. So my equilibrium expression is going to be equal to products over reactants. So it's going to be x times x over 0.30x times 0.30 minus x. Oops. 0.03 minus x. Oops. So dumb. 0.30 minus x, and again 0.30 minus x. Okay, now we have to sort this out. Is the K value given to us? Yes, the K value is given to us, which is 2.50 is going to be equal to, is asking for what are the equilibrium concentration for all of them. This is what they're interested in. Okay, so 2.50 is the K value. So the top becomes x squared and the bottom becomes what? But bottom becomes 0.30 minus x squared. And that can go with x over 0.30 minus x whole square. And in order to solve that, what we can go for is to take the square root on the left-hand side. That means it's going to be the 2.50 is equals to x over, we do not really need to use quadratic equation every time. We can just sort it out without that, but depends on where you are, what you are doing. In the previous example, we must have used the quadratic equation. Here we can go without the quadratic equation. So once that is the situation here, that turns out to be 1.581 is equals to x over 0.30 minus x, and that means it is equals to 2.581x is equals to 0.4743. Eventually, the value of x is equals to 0.1840 molar. Now we need to go into the equilibrium row of the ice chart, and we know that there the concentration of the two reactant was 0.30 minus x. So we have to subtract this value from there. So I'm going to say the concentration of CO2 is equals to the concentration of H2, because the mole-mole ratio is the same. So it's going to be equal to 0.30 minus 0.1840 molar. Whatever the answer is going to be here. And I'm going to say that the concentration of, and because it's just 1:1 mole ratio, so I can say the concentration of H2O, we are considering H2O because it's in its gaseous phase, not in its liquid phase, is equals to CO is equal to the value of X here. Okay, and you can just subtract it and get the value here, whatever the value is. Shifting equilibria, Lechitier's principle, as I told you, that there might be a disturbance in the equilibrium and we can compensate that. So what we do actually to disturb the, what may be the reasons for the disturbance in the equilibrium, that there is probably an addition of a reactant or a removal of a reactant. And this goes exactly for the product, that you are adding more product and taking out the products from the chemical reaction, then the equilibrium will be disturbed because the concentrations are changing. It doesn't mean that the equilibrium that is achieved later on is going to give you a different value, but that system is not at equilibrium at that point and needs to go into the equilibrium and get the same value for the equilibrium. Changing pressure is also changing the concentration, and then changing the temperature is going to give you an entire different value for the K. So adding and removing a reactant or product has a profound effect on the equilibrium. So if a chemical equilibrium is disturbed by adding a reactant or product, the system will proceed in the direction of the consumed part of the added species. Okay, wherever it's going to be the direction. So if the chemical equilibrium is disturbed by removing means you are lowering the concentration. So the reaction is going to move towards where you are removing it from. Okay, it proceeds in the direction that restores part of the removal species. So the process is to restore the equilibrium so that the K becomes equal to Q. Adding or removing pure liquid or solid has no effect on the system unless all the liquid or solid is removed. Okay, keep that in your mind. So what is going on? Let's say it's a good example to discuss that what's going on. If I add more N2O4, what will happen? Will temporarily cause Q to be less than K because it now wants to go towards the left-hand side, right-hand side here. So that will be the direction of the reaction. The reaction will proceed in the forward direction to restore the equilibrium. Adding NO2, now at this time I'm adding this here. So that is going to lead to have a larger value of Q, means the system is product heavy and it wants to move back in the reverse direction. So now removing, if we remove this is high in concentration. It means the Q is larger than K and proceed in the reverse direction. If we remove the product here, then it means this is heavy, and this heavy means Q is less than K, and it's going to go in the forward direction. So pressure changes also have effect. A change in pressure of system at equilibrium will sometimes affect the position of the equilibrium. Okay, so you will also do the practice problem where you have to calculate. Let's say you are going to start from calculating the equilibrium concentration is one of the thing that we are doing, and calculating K is the other thing that we are doing. So once we are able to calculate all these equilibrium concentrations, and if the K is not given to us, they're asking us to calculate K, we can actually calculate the K by putting the values in the K expression. So know that we can do both things. Sometimes K is already given to us, sometimes we are calculating the K. So when the K is given to us, they're interested in the concentration of a species at the equilibrium. So we know that the volume pressure change also changes the concentration. So there will be a disturbance in the equilibrium. Okay. So a change in the pressure of system at equilibrium will sometimes affect the position of the equilibrium. Why? An effect in the position of the equilibrium will only occur when the reaction contains gas phase species. That is important. And the delta N is not equal to 0. So you remember we were discussing this KP, KP is equals to KC and RT. So if the delta N is 0, then KP is equals to KC. the value is exactly equal to Kc, because raised to the power 0 means 0 for this part. Okay, so we just get rid of that, and that becomes equal to this. As I said, changes in the temperature has the most significant effect. You increase the temperature, you increase the heat. The equilibrium responds in a fashion that consumes the added heat. Changing the temperature of a system results in the change in the value of equilibrium. That is the only thing that changes. The concentration never changes. Initial concentration never changes the value of equilibrium, but the temperature does. If the forward reaction is exothermy, what does that mean? It's giving off the heat. Heat is being released. Then K decreases as the temperature increases. But if the forward reaction is heat, it's going to up. If the forward reaction gains heat, then K increases as the T decreases. And this is the entire chart that you can go through to find yourself like what you are looking at, the relationship between the disturbance and what will happen to the K value, if there is going to be an effect or it's not going to be an effect on the K value itself, and the direction of the reaction and observe changes as it is restored. Catalysts do not affect equilibrium. Okay, it just speeds the rate of the reaction. Okay, keep that in your mind. A catalyst causes the system to reach equilibrium more quickly, but a catalyst does not affect the equilibrium concentrations or value of the equilibrium constant at all. That's all for this chapter. I hope you have watched the videos, you have read the material that is provided to you. Next week is going to be the exam. So I'm going to see you guys in the lab at 1. Guys have question for me? I might be late for 15 minutes, so please bear it with me. You can also be late for 10 and 15 minutes here and there. That's like that. It's not like a, but it's just the 15 minutes range that you can be here and there. Please do not come at 2 p.m.